On October 29, 2025, at precisely 14:23 UTC, something broke. Not a machine, not a satellite, something far more fundamental. Our understanding of how objects move through space, a framework we've trusted for over 3 centuries, suddenly had a crack in it. NASA's Jet Propulsion Laboratory, the same team that guides rovers on Mars and keeps the Voyager probes on course billions of miles away, recorded data that made them double check their instruments, then triple check, then call other observatories to confirm. The data was correct, the math was right, the object was wrong. 3I Atlas, the third interstellar visitor. Humanity has ever detected was accelerating. Not because of gravity, not because of any force their equations could account for. The object, a chunk of rock and ice the size of a small mountain, was pushing itself through space in ways that shouldn't be possible. And when scientists calculated what would need to be happening for this acceleration to make sense, they got an answer that made some of them question whether they'd chosen the right career. Let me give you the exact numbers because precision matters here. 3I Atlas was 203 million kilometers from the Sun at its closest approach, what astronomers call perihelion. At that moment, tracking data showed the object was 4 arcseconds away from where gravitational calculations said it should be. Now, 4 arcseconds might sound like nothing. It's a tiny angle, about 1/900th of a degree. But when you're tracking something 203 million kilometers away, 4 arcseconds translates to roughly 3,900 kilometers of deviation. That's nearly the distance from New York to London. And that deviation wasn't random drift or measurement error. It was systematic, consistent, real. The acceleration causing this deviation works out to about 0.02 millimeters per second squared. I know that sounds microscopic, almost laughably small, but here's what that tiny number actually means in practice. Every single second, the object's velocity changes by 2/100ths of a millimeter per second. Sounds insignificant, right? But space is patient and physics is relentless. After one day, that tiny push has changed the velocity by 1.73 meters per second. After 1 month, the cumulative effect has shoved 3I Atlas off its predicted course by 80,000 kilometers. That's more than 6 times the diameter of Earth. That's not a rounding error. That's a fundamental problem. The acceleration has 2 components, and both of them matter. There's a radial component pushing the object away from the Sun at about 135 kilometers per day squared, which adds up to roughly 60,000 kilometers per month of outward drift. Then there's a transverse component, pushing sideways at 60 kilometers per day squared, contributing another 27,000 kilometers of lateral movement. This object isn't just drifting in one direction like a boat caught in a current. It's being actively pushed outward and sideways. Simultaneously, as if invisible hands are steering it away from the Sun while also nudging it perpendicular to its path. Before anyone starts building a bunker or panic buying supplies, let me be absolutely clear about something. This acceleration is not sending 3I Atlas toward Earth. I know that's probably the first thing that crossed your mind, and I want to eliminate that fear immediately. The trajectory, even with this mysterious acceleration, takes the object past Jupiter in March 2026, and then it leaves our solar system forever. We are not in danger. This is not an impact scenario. This is something far more interesting than a disaster movie. This is a scientific mystery of the highest order, and scientific mysteries are infinitely more fascinating than catastrophes. So what exactly is non-gravitational acceleration? Let me break this down in a way that makes intuitive sense. When you throw a ball, gravity pulls it down in a perfectly predictable arc. We've understood this since Newton watched an apple fall, or so the story goes. Every object in space follows these same rules. The sun's gravity pulls things inward, the object's momentum carries it forward, and the result is a curved path we can calculate with extraordinary precision. We use these calculations to land rovers on Mars within a few meters of our target. We use them to slingshot probes around planets to reach the outer solar system. We use them to predict where asteroids will be decades from now. These equations work. They've been tested millions of times. But 3I Atlas isn't following the script. Imagine that ball you threw suddenly had tiny invisible rockets firing on it. It would veer off course in ways that Newton's equations alone can't predict. That's what's happening here. Something is pushing this object beyond what the sun's gravity dictates. And for any natural space object, there's really only one known mechanism that can create this kind of push. The natural explanation is outgassing. Here's how it works. Comets are essentially dirty snowballs, mixtures of ice and rock that formed billions of years ago. When a comet approaches the sun, solar radiation heats its surface. The ice doesn't melt in the vacuum of space. Instead, it sublimates, transforming directly from solid to gas. This gas shoots off the surface at high speeds, carrying dust particles along with it. That's what creates the beautiful tails we see on comets, those magnificent streaks of light stretching millions of kilometers across the sky. But here's the physics part that matters for our mystery. When gas shoots off the surface, it's like a tiny rocket engine. For every action, there's an equal and opposite reaction. Gas shoots one way, the comet gets pushed the other way. This is how rockets work. This is how comets accelerate. This is completely normal, completely understood, completely expected. Scientists have observed this phenomenon hundreds of times with dozens of different comets. The math always checks out. More gas production equals more acceleration. It's reliable, it's predictable, it's physics. So when 3I Atlas started accelerating, the natural assumption was simple. It must be outgassing. Just find the gas cloud, measure it, confirm the numbers match, write a paper, move on to the next object. Simple, straightforward, boring science. Except when they went looking for that gas cloud, things got very unboring very quickly. The timeline of this discovery matters because it shows how the mystery deepened over time, not through speculation, but through careful observation. 3I Atlas was first spotted in July 2025 by the Atlas Survey Telescope System in Hawaii. Initial trajectory calculations immediately flagged it as special. The orbit was hyperbolic, meaning it wasn't gravitationally bound to our sun. This thing came from somewhere else, from another star system entirely. It was only the third such object ever detected, after Oumuamua in 2017 and Borisov in 2019. The astronomical community was excited but not alarmed. Another interstellar visitor. Another chance to study material from beyond our solar system. Through August and September, telescopes tracked it routinely. Scientists noticed early on that the object was brightening faster than expected as it approached the sun, but initial assessments attributed this to its unusual composition. Maybe the surface was more reflective than typical comets. Maybe the ice was purer. Reasonable assumptions. Nothing to lose sleep over. Then came October. As 3I Atlas approached its closest point to the sun, multiple observatories locked on with their most sensitive instruments. Predictions were made with extreme precision. Here's exactly where it will be at perihelion. Here's the path it will follow afterward. These predictions were based on the same physics that has successfully tracked every single object in our solar system for centuries. October 29th arrived. Perihelion occurred, and 3I Atlas wasn't where it was supposed to be. The initial reaction was disbelief. Recalculate. Recheck the data. Maybe a software glitch. Maybe an input error. But no. Independent observatories confirmed the same deviation. The Pan-STARRS telescope in Hawaii saw it. The Catalina Sky Survey in Arizona saw it. The Very Large Telescope in Chile saw it. This wasn't instrument error. This was real. JPL filed their official report. The object was accelerating at 0.02 millimeters per second squared. Non-gravitational acceleration confirmed. Now find the outgassing that explains it. That's where the real problem began. Why should anyone care about a weird space rock? Let me explain what's actually at stake here, because this goes far beyond astronomical curiosity. The physics we're using to track 3I Atlas is the same physics that governs everything we do in space. Every satellite orbiting Earth, every GPS signal you use to navigate, every weather forecast based on satellite data, all of it relies on our ability to predict exactly where objects will be in space at any given moment. We've been refining these calculations since Newton published his Principia in 1687. That's 338 years of building confidence. Einstein refined the equations in 1915 with general relativity, accounting for effects Newton couldn't have imagined. We've tested these laws under extreme conditions. They work at Mercury, the closest planet to the Sun. They work at Neptune, nearly 3 billion miles away. They work for asteroids, comets, moons, planets, and spacecraft. The margin of error is essentially zero for practical purposes. So when an object shows up that doesn't follow these rules, it's not just scientifically interesting, it's potentially paradigm shifting. Either there's a force acting on this object that we can measure and confirm, like outgassing, or there's something happening that our current physics can't fully explain. Neither option is comfortable. An unnamed JPL engineer speaking off the record captured the anxiety perfectly. If we can't explain why a 6-kilometer rock is accelerating, how confident can we be in the rest of our predictions? It's a fair question. And it's a question that's keeping a lot of very smart people up at night right now. The last time an observation broke our physics models this badly was when scientists noticed that Mercury's orbit didn't quite match Newtonian predictions. The planet's closest approach to the Sun shifted slightly over time in ways Newton's equations couldn't account for. It took Einstein and the general theory of relativity to explain it. That single anomaly led to a complete revolution in our understanding of space, time, and gravity. What theory will we need to explain 3I Atlas? Before we can truly grasp why 3I Atlas is impossible, we need to understand why everything else in space is so beautifully predictable. And I promise, this is simpler than you think. You don't need a physics degree. You don't need to understand calculus. You don't need to have aced your science classes. You just need to understand one fundamental concept, and then the impossibility becomes crystal clear. Once you see it, you can't unsee it. The anomaly will jump out at you like a spelling error in a headline. In space, there's no air resistance, no friction, no wind, no invisible forces slowing things down or pushing them sideways. Once an object is moving, only one thing affects its path: gravity. That's it. Just gravity. The sun pulls things toward it, planets tug on passing objects, moons influence their surroundings. But all of these gravitational influences are completely, perfectly, mathematically predictable. If you know where everything is and how massive each object is, you can calculate exactly where anything will be at any point in the future. Not approximately. Exactly. Think of the solar system as the universe's most precise billiard table. Once the balls are in motion, their paths are determined entirely by the forces acting on them. No surprises, no randomness, pure mathematics. We've been using this principle since Newton published his Principia Mathematica in 1687. That's 338 years of testing, 338 years of refinement, 338 years of proving that these equations work with almost supernatural precision. We use this principle to predict where asteroids will be in 100 years. We used it to land the Curiosity rover inside a specific crater on Mars after an 8-month journey through space covering 352 million miles. Think about that for a moment. We launched a car-sized robot, hurled it through the void for 8 months, and placed it within a few meters of our intended target on a planet tens of millions of miles away. That's how reliable orbital mechanics is. That's how confident we are in these equations. We used the same physics to send New Horizons past Pluto within 70 kilometers of its target after traveling for 9.5 years. 9.5 years. The spacecraft journeyed 3 billion miles, and we knew exactly where it would be, when it would arrive, and how fast it would be moving. The margin of error was essentially zero. These aren't flukes or lucky guesses. This is precision engineering based on mathematical laws that have never failed us. Every GPS satellite orbiting Earth, every weather satellite sending data, every communication satellite beaming television signals, all of them rely on these exact same orbital mechanics. Your phone knowing your location depends on our ability to track satellites with precision measured in centimeters. That's the level of confidence we have in this physics. Now, acceleration in physics doesn't just mean speeding up. This is a common misconception that trips people up. In everyday language, we use acceleration to mean going faster. But in physics, acceleration means any change in velocity, and velocity includes both speed and direction. So if an object speeds up, that's acceleration. If it slows down, that's acceleration in the negative direction, sometimes called deceleration. If it changes direction while maintaining speed, that's also acceleration. Any change in how fast you're going or where you're heading counts as acceleration. For 3I Atlas, the measured acceleration of 0.02 millimeters per second squared means its velocity is changing by that amount every second. And remember, this has two components. The radial component pushes away from the sun at 135 kilometers per day squared. Over the month surrounding perihelion, this alone accounts for roughly 60,000 kilometers of outward drift. The transverse component pushes sideways at 60 kilometers per day squared, adding another 27,000 kilometers of lateral displacement. Let me make those numbers more visceral. After just 1 month, this seemingly tiny acceleration has shoved the object 80,000 kilometers off its gravitationally predicted course. That's more than 6 times the diameter of Earth. Imagine launching a satellite and having it end up 6 Earth diameters away from where you expected. That's not a rounding error. That's not instrument noise. That's a fundamental failure of prediction. Either your physics is wrong or something is actively pushing the object. There is no third option. Here's why this breaks everything. In a vacuum with no forces except gravity, this acceleration is physically impossible. Something must be pushing. And according to Newton's third law, arguably the most tested law in all of physics, for every action there's an equal and opposite reaction. If the object is being pushed forward, something must be shooting backward. If it's accelerating left, something must be ejecting right. The push requires a reaction. Every rocket that's ever launched works on this principle. Every jet engine, every fish swimming through water. The law is universal and inviolable. So where's the reaction for 3I Atlas? Where's the push coming from? What's being ejected that creates this thrust? To understand the expected answer, let's look at what comets normally do. Comets are time capsules from the formation of our solar system, chunks of ice, dust, and rock that never coalesced into planets. They formed about 4.6 billion years ago in the outer reaches of the solar nebula, the cloud of gas and dust that collapsed to form our sun and planets. They've remained virtually unchanged since then, frozen samples of the original material from which everything in our solar system formed. Most comets spend their existence in 2 regions far from the sun: the Kuiper Belt, just beyond Neptune's orbit, and the Oort cloud, a spherical shell of icy bodies extending perhaps halfway to the nearest star. Out there, temperatures hover just a few degrees above absolute zero. Ice remains ice. Nothing changes. Nothing evolves. They're frozen in time. But sometimes gravitational perturbations from passing stars or the galaxy's tidal forces nudge a comet out of its distant home. It begins falling sunward, picking up speed as gravity accelerates it. The journey can take thousands or even millions of years. As it approaches the inner solar system, things get interesting. As a comet approaches the sun, solar radiation heats its surface. The intensity of sunlight increases dramatically. At Earth's distance from the sun, we receive about 1,400 watts per square meter of solar energy, enough to power 14 100-watt light bulbs for every square meter. A comet approaching inside Earth's orbit receives even more. This energy warms the surface, and the ice within begins to respond. The ice doesn't melt because there's no atmospheric pressure in space. Without pressure, liquid water can't exist. Instead, the ice sublimates directly from solid to gas. Water ice becomes water vapor. Carbon dioxide ice becomes carbon dioxide gas. Carbon monoxide ice becomes carbon monoxide gas. This phase transition happens at the molecular level. Solid molecules gain enough energy to break their bonds with neighboring molecules and escape directly into space as gas. These gases shoot off the surface at tremendous speeds, typically between 300 and 1,000 meters per second. That's 670 to 2,200 miles per hour. The gas doesn't drift away gently, it rockets off the surface, and it carries dust particles along with it. Small grains of rock and metal embedded in the ice get swept up in the gas flow, creating streams of material leaving the nucleus. This outgassing creates the coma, that fuzzy glowing cloud around a comet's nucleus. The coma can extend tens of thousands of kilometers, sometimes larger than Jupiter. It also creates the tail, or rather the tails, since comets have two distinct ones. The dust tail curves gently, pushed by solar radiation pressure. It's made of those particles swept up by the gas, reflecting sunlight as they drift away from the nucleus. The ion tail points straight away from the sun, sculpted by the solar wind. It's made of ionized gas molecules, glowing as they interact with solar radiation. These features can stretch for millions of kilometers, making comets some of the most spectacular objects in our sky. But the physics that matters for our mystery is the thrust. When gas shoots off one side of a comet's nucleus, it's exactly like a rocket engine firing. The gas goes one way, the comet gets pushed the other way. Conservation of momentum. This is literally how spacecraft propulsion works. Every kilogram of gas ejected at 500 meters per second transfers momentum to the comet, nudging it slightly off its purely gravitational path. This is non-gravitational acceleration, and we see it in virtually every comet that passes close to the sun. Take Comet Halley as an example. When it last visited the inner solar system in 1986, it showed a non-gravitational acceleration of about 0.01 millimeters per second squared, half of what we're seeing with 3I Atlas. And Halley had a massive, spectacular tail visible to the naked eye from Earth. The European Space Agency sent spacecraft to observe it up close. The Giotto probe flew within 596 kilometers of Halley's nucleus, photographing jets of gas streaming off the surface. Gas production was measured at hundreds of thousands of kilograms per second. The coma extended hundreds of thousands of kilometers. Everything matched. The acceleration correlated perfectly with the observed outgassing. Scientists could plug the mass loss rate and ejection velocity into their equations and predict the acceleration precisely. The math checked out. Physics worked exactly as expected. Or consider Comet 67P, officially named Churyumov-Gerasimenko, which the European Space Agency studied up close with the Rosetta mission from 2014 to 2016. This was the first time humanity orbited a comet and landed a probe on its surface. Scientists literally photographed jets of gas shooting off the surface. They could see the eruptions. They measured the IED acceleration over months of observation. They calculated the gas production independently through spectroscopy. Everything aligned. The thrust matched the ejection. The numbers made sense. When 67P showed non-gravitational acceleration, the science team could point to specific outgassing events and say, that's what caused it. Cause and effect. Action and reaction. This is how comets work. This is established science, not theory. We've observed hundreds of comets over centuries. Every single one that shows non-gravitational acceleration also shows proportional outgassing, without exception. The correlation is perfect. This isn't a hypothesis waiting for confirmation. This is observed, measured, repeatedly verified fact. The gas explains the thrust. The mass loss rate times ejection velocity equals the force. The force divided by the mass gives the acceleration. The math is simple, the physics is sound, the observations confirm the equations, over and over and over. So 3I Atlas should be doing the same thing. It's accelerating, therefore it must be outgassing. Find the gas, measure it, confirm the correlation, done. Publish a paper noting its unusual composition or surface properties, add it to the database, move on to the next object. Simple, straightforward, routine science. Except when they went looking for that gas cloud, things got very unboring very quickly. But wait, you might be thinking, this is an interstellar object. Maybe it's different. Maybe it's made of something exotic that we've never seen before. This is a reasonable hypothesis, and scientists have considered it carefully. In fact, it was one of the first explanations proposed. Interstellar objects have a different history than our local comets. They formed around other stars, with potentially different chemistry. The elements might be in different proportions. The compounds might be unusual. They were ejected into interstellar space through gravitational interactions, perhaps from a planetary system that looked nothing like ours. Maybe their parent star was larger than our sun, or smaller, or older, or had different abundances of heavy elements. After ejection, they've traveled for millions or even billions of years through the void between stars. This journey changes things. The surface gets processed by cosmic rays, high-energy particles that permeate interstellar space. Cosmic rays can alter surface chemistry, break molecular bonds, create new compounds. The surface material might be unlike anything we find on solar system objects. The internal structure could be organized differently. So yes, 3I Atlas might be made of something we've never encountered before. That's actually quite likely given its origin. Scientists hope this might solve the puzzle. Perhaps the gas is simply invisible to our telescopes. Perhaps it's a type of outgassing we can't detect easily. Maybe nitrogen or carbon monoxide sublimating without leaving obvious spectral signatures. Maybe some exotic ice we haven't imagined that produces transparent gas. The hope was reasonable. Different origin could mean different composition. Different composition could mean different outgassing behavior. But here's the fundamental problem that no exotic composition can solve, and this is the crux of everything. No matter what the gas is made of, the physics of momentum conservation remains absolute. This law doesn't care about composition. It doesn't care about origin. It doesn't care about our assumptions or hopes. To accelerate a 33 billion ton object at 0.02 millimeters per second squared, you need a specific amount of mass being ejected at a specific velocity. The type of gas doesn't change the quantity required. Whether it's water vapor, nitrogen gas, hydrogen gas, carbon dioxide, or something we've never identified, the momentum equation remains the same. Force equals mass times acceleration. Force also equals the mass loss rate multiplied by the ejection velocity. These equations aren't theories we're testing. They're laws that have never been violated in any experiment ever conducted anywhere in the universe, as far as we know. Rearranging these equations shows that the mass loss rate must equal the object's mass times its acceleration, divided by the gas ejection velocity. When you plug in the numbers for 3I Atlas, and we'll go through this calculation explicitly in the next act, you get a mass loss rate that should be blindingly obvious to detect. Trillions of kilograms of gas over the perihelion month, a cloud the size of Earth or larger surrounding the nucleus, brightness that rivals the most spectacular comets ever observed. The gas isn't just undetected. If it existed in required quantities, it would be impossible to miss. Our telescopes aren't searching for a needle in a haystack. They're searching for a mountain in an empty parking lot. And they're not finding it. That's not a measurement problem. That's not an instrument sensitivity issue. That's not about looking in the wrong wavelength. That's a fundamental physics problem. The cause doesn't match the effect. The action has no visible reaction. The acceleration exists without the mechanism that should produce it. And this is where things get really interesting. Because if the natural explanation fails, what replaces it? What force could accelerate a 6-kilometer object through space without the visible reaction that physics demands? We've been tracking objects in space for centuries, and we've never seen anything like this. Actually, that's not quite true. We've seen this once before. And that's what makes this even more unsettling. Now we arrive at the part that makes physicists uncomfortable. The actual calculation. The math that reveals why 3I Atlas shouldn't exist as a natural object. And I want to walk you through this step by step, not because I don't trust you to take my word for it, but because understanding the calculation yourself transforms this. From a story you're hearing into evidence you're evaluating. By the end of this, you'll see the exact number that's causing all this scientific anxiety, and you'll understand precisely why it's so damning. Let's establish what we know for certain. These aren't estimates or guesses. These are measured values confirmed by multiple independent observations. First, the mass of 3I Atlas. The nucleus has been measured at approximately 5.1 kilometers in diameter. This isn't speculation. Thermal observations from infrared telescopes gave us this figure. Now, to calculate mass from size, we need density. For typical comets, that's around 0.5 grams per cubic centimeter. That might sound arbitrary, but it's based on direct measurements of other comets, particularly 67P, which Rosetta studied up close. Using standard geometry, a sphere 5.8 kilometers across has a volume of roughly 100 cubic kilometers. Multiply by the density, and we get approximately 33 billion metric tons. In scientific notation, that's 3.3 times 10 to the 13th kilograms. Now, you might worry that this density estimate could be wrong. Fair concern. But here's why it doesn't matter much. Even if we're off by a factor of 2 in either direction, the fundamental problem doesn't disappear. The numbers are so extreme that reasonable variations in density don't change the conclusion. We'll see why in a moment. Second, the measured acceleration. This is our most confident number because it comes directly from the trajectory deviation. 0.02 millimeters per second squared, or in scientific notation, 2 times 10 to the negative fifth meters per second squared. Multiple observatories confirm this value. It's not debatable. So here's our question. If outgassing is causing this acceleration, how much gas needs to be shooting off this object every second? The physics principle at play is conservation of momentum, one of the most fundamental laws in physics. It's never been violated in any experiment ever conducted. Here's how it works in plain language. You're standing on a frozen lake wearing ice skates. No friction, you're holding a heavy backpack. You throw that backpack as hard as you can in one direction. What happens? You slide backward in the opposite direction. The heavier the backpack and the harder you throw it, the faster you slide. That's momentum conservation. The total momentum of the system, you plus the backpack, stays the same. This is exactly what should be happening with 3I Atlas. Gas shoots off the surface in one direction, the entire object gets pushed in the opposite direction. The mass of gas times its velocity must equal the mass of the object times its acceleration. This relationship is absolute. It's not a theory anymore. It's observed physics. The mathematical formula is straightforward. Force equals mass times acceleration. We know the mass and the acceleration, so we can calculate the force. That same force also equals the mass loss rate, how much gas is leaving per second, multiplied by the velocity at which it leaves. Rearranging, the mass loss rate equals the object's mass times its acceleration, divided by the gas ejection velocity. Let's run the numbers with 3 different scenarios, each giving the natural explanation the maximum benefit of the doubt. Scenario 1 uses conservative, typical values. Gas ejection velocity of 300 meters per second. This is normal for water ice sublimation on comets. We've measured this directly. Object mass of 3.3 times 10 to the 13th kilograms. Acceleration of 2 times 10 to the negative fifth meters per second squared. Plugging these in, the mass loss rate equals 3.3 times 10 to the 13th multiplied by 2 times 10 to the negative fifth, all divided by 300. That gives us 2.2 times 10 to the 6th kilograms per second. Let that number sink in. 2.2 million kilograms per second. Every single second, 2,200 metric tons of gas must be shooting off this object. Not per hour, not per day. Per second. How much is that over time per day multiplied by 86,400 seconds? That's 190 billion kilograms daily. Over the month surrounding perihelion when this acceleration was measured, we're talking about 5.7 trillion kilograms. 5.7 billion metric tons of gas. Remember, the entire object only weighs 33 billion tons. This means 3I Atlas would need to lose roughly 17% of its total mass in a single month just to create the observed acceleration. But maybe I'm being unfair. Let's try scenario 2 with more generous assumptions. Suppose the gas is ejecting faster than typical. Much faster. Let's say 1,000 meters per second, which would require exotic lightweight molecules moving at extreme speeds. Running the same calculation with this higher velocity, we get a mass loss rate of 660,000 kilograms per second. Better, but still enormous. Over 1 month, that's 1.7 trillion kilograms. About 5% of total mass. Still not satisfied? Let's go to scenario 3, the absolute extreme. Gas ejection at 2,000 meters per second. This is pushing the boundaries of what's physically realistic for any natural sublimation process. At this velocity, the mass loss rate drops to 330,000 kilograms per second. Per month, that's 850 billion kilograms. Still nearly a trillion kilograms of gas. Notice something important. Despite varying our assumptions by almost a factor of 7, we consistently get mass loss rates in the hundreds of thousands to millions of kilograms per second. We consistently get monthly mass losses in the hundreds of billions to trillions of kilograms. The specific number changes, but the order of magnitude stays the same. We're always looking at staggering amounts of gas. So why is this a problem? Why can't we just accept that 3I Atlas is losing this much mass? Because a trillion kilograms of gas doesn't quietly vanish into space. Gas expands. Gas reflects sunlight. Gas creates an enormous, brilliant cloud around the nucleus. At these mass loss rates, 3I Atlas should be surrounded by a coma, a cloud of gas and dust, at least 50,000 to 100,000 kilometers in diameter. For reference, Earth's diameter is about 12,700 kilometers. We're talking about a gas cloud nearly 10 times larger than our planet, glowing brilliantly as it reflects sunlight, easily visible to any half-decent telescope pointed in its direction. Consider Comet Hale-Bopp, which graced our skies in 1997. It It was one of the brightest comets of the 20th century, visible to the naked eye for a record 18 months. Its coma stretched 2.5 million kilometers across. Gas production at peak was measured at around 150,000 kilograms per second. That's it. 150,000 kilograms per second created a spectacle visible without telescopes from Earth's surface. 3I Atlas, if naturally outgassing to match its acceleration, should be producing 10 to 15 times more gas than Hale-Bopp at peak. We should see a coma as bright as a small moon. We should detect it without sophisticated equipment. It should be obvious, unmissable, spectacular. What do our best telescopes actually see? Hubble has detected a coma around 3I Atlas. Good news, right? The natural explanation is saved? Not quite. The coma is there, but it's weak. Estimated gas production, based on the observed brightness, comes to maybe 50,000 to 100,000 kilograms per second. That sounds like a lot until you remember we need 600,000 to 2,000 kilograms per second minimum. We're seeing 20 to 40 times less gas than required. Ground-based spectroscopy, which looks for specific chemical fingerprints of gases, tells the same story. Some carbon compounds detected, some water signatures, but amounts are woefully insufficient. The gas that exists can't explain the acceleration. The physics doesn't balance. Maybe you're thinking, the gas is there but invisible to our instruments? Maybe it's some exotic molecule we can't detect? This objection seems reasonable until you think about it carefully. All gas has mass. All mass interacts with light at some wavelength. James Webb sees infrared. Hubble sees optical and ultraviolet. Radio telescopes detect molecular emissions directly. We're looking across the entire electromagnetic spectrum with the most sensitive instruments ever built. More importantly, even invisible gas creates observable effects. Gas streaming off a nucleus at hundreds of meters per second creates drag on dust particles. We should see the dust even if we miss the gas. Gas expanding outward creates pressure effects. Gas absorbs or emits at characteristic frequencies. We have multiple independent ways to detect outgassing, and all of them are returning insufficient results. Here's another objection that sounds clever but doesn't hold up. Maybe our mass estimate is wrong. Maybe 3I Atlas is much lighter than we think, and therefore needs less gas to accelerate. Let's test this. For the observed gas production of around 50,000 to 100,000 kilograms per second to create the measured acceleration, the object would need to weigh approximately 500 million tons. That's 60 times less than our current estimate, but we've measured the size directly. The nucleus is 5.8 kilometers across. An object that size with only 500 million tons of mass would have a density of about 0.08 grams per cubic centimeter. For perspective, water has a density of 1 gram per cubic centimeter. Styrofoam is around 0.05 grams per cubic centimeter. We'd be claiming this object is 6 times less dense than styrofoam. That's not physically realistic for any natural celestial body. It would essentially be empty space, loosely held together, and such a structure couldn't survive the tidal forces of passing close to the sun. The math is unforgiving. The measured acceleration requires massive outgassing. Massive outgassing should be visible. We don't see it. Therefore, either our physics is wrong, our observations are wrong, or the acceleration isn't coming from outgassing. The first option would require overturning centuries of confirmed physics. The second option has been ruled out by multiple independent observations. That leaves the third option, uncomfortable as it may be. Harvard's Avi Loeb published these same calculations in November 2025. He's not some fringe figure. He's the longest-serving chair of Harvard's astronomy department. He's published over 1,000 scientific papers. He knows orbital mechanics as well as anyone on Earth. His conclusion was stark. If upcoming observations don't reveal a coma proportional to the observed acceleration, we must seriously consider that the acceleration mechanism is not natural outgassing. He's not claiming aliens. He's claiming something more fundamental. The data doesn't fit our theory. Either find data that does fit or find a new theory. That's how science works. That's how science has always worked, and right now the theory is failing. October 19th, 2017. 8 years before 3I Atlas entered our solar system, another impossibility arrived. The Pan-STARRS telescope in Hawaii, the same facility that would later contribute to tracking 3I Atlas, spotted a faint moving object. Initial calculations showed something extraordinary. This object wasn't bound to our sun. It was the first confirmed visitor from interstellar space, a messenger from another star system, the first scout from the cosmic ocean beyond. They named it Oumuamua, a Hawaiian word meaning roughly scout or messenger from afar reaching out to us. The name was poetic. The reality was bewildering. First, the shape. Oumuamua was elongated to an extreme degree never seen in any natural solar system object. The aspect ratio was approximately 10 to 1. Imagine a cigar 400 meters long but only 40 meters wide. Or alternatively, picture a pancake 400 meters across but only 40 meters thick. The actual shape remains debated, but either interpretation requires an object unlike anything we've cataloged in our solar system. Asteroids are typically potato-shaped. Comets are lumpy snowballs. Nothing is 10 to 1 elongated. Nothing rotates like Oumuamua did, tumbling end over end every 7.3 hours. Second, the surface. Oumuamua appeared completely dead. No coma, no tail, no fuzzy glow of gas surrounding it. When it passed close enough to the sun that any ice should have sublimated violently, it showed no signs of outgassing whatsoever. Spectral analysis suggested a reddish surface, consistent with extreme age and cosmic ray bombardment over millions of years. The object looked ancient, weathered, and completely inert. Third, and most troubling, the acceleration. In June 2018, a paper published in Nature sent ripples through the astronomical community. Careful analysis of Oumuamua's trajectory revealed something disturbing. The object was accelerating away from the sun in ways that gravity alone couldn't explain. The magnitude was about 5 times 10 to the negative 4th centimeters per second squared, or roughly 0.05 millimeters per second squared. That's about 1/4 the acceleration we're seeing with 3i Atlas, but it's still completely anomalous for an object showing no outgassing. The immediate response was predictable. It must be outgassing. We just can't see it. Maybe it's coming from a small area we can't resolve. Maybe the gas is invisible to our wavelengths. Maybe the composition is exotic. Sound familiar? NASA pointed the Spitzer Space Telescope at Oumuamua. Spitzer was specifically designed to see infrared radiation, the heat signature that any outgassing would produce. It was the most sensitive instrument available for detecting the thermal emissions of sublimating ice. The telescope observed Oumuamua carefully, looking for any hint of gas production. The result? Nothing. Zero. No detection whatsoever. No infrared excess, no heat signature. No evidence of any material leaving the object. Whatever was accelerating Oumuamua, it wasn't visible outgassing. The object was pushing itself through space with no apparent reaction mass. Scientists scrambled for explanations. The stakes were high. Admitting we couldn't explain the acceleration opened doors to hypotheses that mainstream astronomy found uncomfortable. Surely there was a natural explanation. There had to be. First came the nitrogen ice hypothesis. Researchers proposed that Oumuamua might be a chunk of solid nitrogen, similar to the surface of Pluto. Nitrogen ice is transparent when it sublimates, potentially invisible to our instruments. The low density would mean the object could be mostly nitrogen ice, light enough that solar radiation pressure could provide additional acceleration. The problems emerged quickly. For Oumuamua to be a nitrogen ice fragment, it would need to originate from a Pluto-like object in another solar system. Such objects are incredibly rare. The probability of one being ejected toward our solar system, surviving the interstellar journey, and arriving just when we could detect it was astronomically low. Worse, even nitrogen gas should produce some detectable signature, and Spitzer found nothing. Next came the hydrogen iceberg proposal. Perhaps Oumuamua was made of frozen molecular hydrogen, which has the lowest density of any solid. This would make it extremely light, allowing small forces to create large accelerations. Hydrogen sublimates readily, providing thrust. This explanation collapsed under scrutiny too. Hydrogen ice cannot survive the interstellar journey. Cosmic rays would destroy it over millions of years. The evaporation rate is too high, even in the cold of interstellar space. No known mechanism could create such an object and keep it intact long enough to reach us. Then came the fractal dust aggregate theory. Maybe Oumuamua was essentially a cosmic dust bunny, an extremely porous structure with density so low that solar radiation pressure alone could accelerate it, like a dandelion seed catching the wind. But such a fragile structure would be torn apart by tidal forces when passing close to the sun. The brightness variations didn't match predictions for such an object. And again, no known formation mechanism could create something so delicate yet so large. One by one, natural explanations were proposed. One by one, they failed under careful analysis. Each solution created more problems than it solved. Each attempt to force Oumuamua into our understanding of natural objects required assumptions so extreme as to be implausible. The scientific community found itself in an uncomfortable position. Conferences featured heated debates. Papers contradicting other papers filled journal pages. Reputations were staked on positions. Some astronomers doubled down on natural explanations, arguing that our imagination simply hadn't found the right exotic mechanism yet. Others quietly wondered if perhaps we were missing something more fundamental. The tension between scientific caution and intellectual honesty became palpable. What made this particularly frustrating was the timing. Oumuamua was discovered after it had already passed its closest approach to both the Sun and Earth. By the time we realized what we were looking at, it was already racing away from us. Every day it grew fainter. Every week our observation window narrowed. Within months, even our most powerful telescopes could barely detect it. The first interstellar visitor humanity ever identified was leaving us with more questions than answers, and we had no way to call it back. Into this vacuum stepped Avi Loeb with a controversial suggestion. In November 2018, he and his postdoctoral researcher, Shmuel Bialy, published a paper in Astrophysical Journal Letters. They proposed that Oumuamua's acceleration could be explained by solar radiation pressure alone, with no outgassing required. But for this to work, the object would need to be extremely thin, less than 1 millimeter thick. A flat sheet of material catching sunlight like a sail. The implication was stunning. No natural process creates objects that thin. Only artificial construction could produce such geometry. Oumuamua might be a light sail, a piece of technology from another civilization. The backlash was immediate and fierce. Astronomers accused Loeb of sensationalism. Careers were built on being serious, cautious, conservative. Suggesting alien technology was career suicide. The scientific establishment pushed back hard. Colleagues who had respected Loeb for decades suddenly questioned his judgment. Invitations to conferences became conditional on not discussing certain topics. The message was clear. Stay in your lane. Don't embarrass the profession. But Loeb's defense was elegant and difficult to refute. He wasn't claiming certainty. He was claiming that artificial origin was no less likely than any natural explanation proposed. Every natural hypothesis had failed. Every natural model had problems. If you're going to consider unlikely natural origins like nitrogen ice from a Pluto-like exoplanet, why not also consider artificial origin? Both are improbable. Neither is proven. Let the data decide. He pointed out something that his critics couldn't easily dismiss. Science advances by considering all possibilities consistent with data, not by ruling out hypotheses because they make us uncomfortable. If we reject artificial origin simply because it sounds fantastical, we're not doing science. We're doing dogma. We're letting our assumptions constrain our conclusions rather than letting evidence guide our understanding. 6 years later, no one has provided a natural explanation for Oumuamua that fully works. The object left our solar system, beyond our ability to study further. The mystery persists. Textbooks mention it with hedged language. Probably a natural object with unusual properties. Probably. That word does a lot of heavy lifting. And now 3I Atlas presents the same puzzle. Acceleration without proportional outgassing. The same impossible physics. The same failing explanations. But here's what makes 3I Atlas even more significant. We have context now. We have comparison. Between Oumuamua and 3I Atlas, we detected another interstellar visitor. 2I Borisov arrived in 2019, the second interstellar object on record. Unlike its predecessor, Borisov behaved like a textbook comet. It had a beautiful tail stretching hundreds of thousands of kilometers. Gas production was clearly visible. Spectroscopy identified water vapor, carbon dioxide, and other familiar cometary signatures. The acceleration matched the outgassing perfectly. Every number added up. Every model worked. Borisov was weird only in its origin. Its behavior was perfectly normal. So we have a sample of 3. First interstellar object shows impossible acceleration without visible outgassing. Second interstellar object behaves completely normally. Third interstellar object shows impossible acceleration without proportional outgassing. That's 2 out of 3. 67%. If this were any other scientific data set, we'd be declaring a pattern. One anomaly is a fluke. 2 anomalies with identical characteristics is a trend-demanding explanation. Consider what this means for statistical analysis. If strange interstellar objects were random flukes, we'd expect most detections to behave normally with occasional oddballs. Instead, the majority of our sample shows anomalous behavior. The normal comet is the outlier, not the strange ones. That inverts our expectations completely. What separates the weird ones from the normal one? Why do Oumuamua and 3I Atlas break our physics while Borisov follows it perfectly? What mechanism could explain acceleration without reaction mass in 2 independent cases? The honest answer is we don't know. But we're no longer dealing with a single strange data point that we can dismiss as cosmic oddity. We're dealing with a repeating phenomenon. And repeating phenomena have causes. Finding that cause might be the most important scientific question of our lifetimes. Or it might be nothing, an artifact of incomplete understanding waiting for a clever theorist to resolve. The pattern also raises questions about what we might detect in the future. With improving telescope technology, we're finding more interstellar objects. The Vera Rubin Observatory, coming online soon, will survey the entire visible sky every few nights. We'll likely detect dozens more interstellar visitors in coming decades. Will they behave normally like Borisov? Or anomalously like Oumuamua and 3I Atlas? The answer to that question might tell us whether we're seeing natural variation or something more systematic. Either way, 3I Atlas isn't going to let us ignore the question any longer. It's bigger than Oumuamua. It's closer than Oumuamua. It's more measurable than Oumuamua. And in the coming weeks, we're going to point every instrument we have at it and demand answers. Whatever those answers turn out to be, they're going to change something fundamental about how we understand our universe. If the acceleration mystery were the only strange thing about 3I Atlas, scientists might find comfort in that simplicity. One anomaly, one puzzle to solve. But the universe rarely offers such clean mysteries. As astronomers trained their instruments on this interstellar visitor, they discovered that the acceleration wasn't an isolated oddity. It was part of a constellation of strange behaviors, each one adding another layer to an already baffling puzzle. The more they looked, the weirder things got. Let's start with brightness. Every comet we've ever studied follows predictable patterns when approaching the sun. As they get closer, they get brighter. This makes intuitive sense. More solar energy means more ice sublimation. More sublimation means more gas and dust. More gas and dust means more surface area reflecting sunlight. The relationship follows. What physicists call a power law. Brightness increases proportionally to distance raised to some negative exponent. For typical comets, that exponent falls between -2 and -3. In practical terms, if you have a comet's distance to the sun, its brightness increases by a factor of 4 to 8. 3I Atlas didn't follow this script, not even close. Its brightness increased following an exponent of -7.5. Let me translate what that means in concrete terms. When the object's distance to the sun decreased by half, its brightness didn't increase 4 to 8 times. It increased roughly 180 times. That's not a subtle deviation from the norm. That's a completely different phenomenon. Consider what this means physically. For brightness to increase that dramatically, something about the object must be changing rapidly as it approaches the sun. Either the surface area reflecting light is expanding explosively, or the reflectivity of the surface is increasing dramatically, or some process is generating light directly rather than just reflecting it. Each possibility has problems. If the brightness comes from expanding gas and dust cloud, we're back to the outgassing issue. Where's all that material coming from? Why can't we detect it in proportions matching the brightness increase? If the surface reflectivity is changing, what physical process could alter albedo so rapidly? Surfaces don't spontaneously become mirrors. And if something is generating light directly, what energy source powers it? What chemical or physical reaction produces photons at this rate? The brightness anomaly correlates suspiciously well with the acceleration anomaly. Both peaked around perihelion. Both showed extreme values unprecedented in cometary science. Whatever mysterious process is causing the unexplained acceleration might also be causing the unexplained brightness increase. These aren't separate mysteries that coincidentally affect the same object. They're connected symptoms of a single underlying phenomenon that we don't understand. Compare this to normal cometary behavior. When comet Neowise graced our skies in 2020, it followed a brightness curve with an exponent around -2.3. Perfectly normal. Its coma expanded as expected. Its tail grew proportionally. Everything matched predictions. Scientists could model its behavior accurately because it behaved like comets are supposed to behave. 3I Atlas isn't giving us that courtesy. Some researchers propose that perhaps the nucleus itself is fragmenting as it approaches the sun. Thermal stress could cause pieces to break off, exposing fresh ice underneath. New surface area could explain increased outgassing and brightness. This hypothesis seems plausible until you examine the data more carefully. If fragmentation were occurring, we'd see multiple brightness centers. We'd detect different pieces moving apart. We'd observe changes in the rotation period as mass distribution shifted. None of these signatures have appeared. The nucleus remains coherent. The brightness increase is uniform and symmetric. Fragmentation doesn't explain the observations. Another suggestion involved phase transitions in exotic surface materials. Perhaps the surface is coated in something that changes crystalline structure when heated, becoming dramatically more reflective. But no known material exhibits such behavior at these temperatures and in vacuum conditions. It's a hypothetical solution to a real problem, and hypothetical solutions that require unknown physics aren't really solutions at all. Now let's add the color anomaly. This one is subtle but profoundly strange. When astronomers analyze the light spectrum from 3I Atlas, they find something unexpected. The object appears blue, not just slightly less red than expected, actually bluer than the sun itself. To understand why this is bizarre, you need to know how light interacts with particles in space. Dust grains scatter blue light more efficiently than red light. This is why Earth's sky appears blue during the day. Sunlight enters the atmosphere. Blue wavelengths scatter in all directions, red wavelengths pass through more directly. The same principle applies in space. Objects covered in dust, which includes virtually everything, appear reddish because dust preferentially scatters away the blue light and lets red through. Every asteroid we've studied shows this reddening effect. Every comet nucleus we've imaged directly appears reddish. Even Oumuamua, despite all its strangeness, showed the red coloring expected from billions of years of dust accumulation and cosmic ray bombardment. Redness is the default state of ancient surfaces in space. 3I Atlas breaks this rule. Its spectrum shows a blue excess. Light reflecting from this object has more blue wavelengths than the sunlight hitting it. That shouldn't happen passively. To appear bluer than your light source, you need to either generate blue light directly or have a surface that selectively absorbs red light while reflecting blue. Neither option is easy to explain naturally. One proposed mechanism involves ionized gases. Certain molecules, when ionized by solar radiation, emit light at specific wavelengths. Carbon monoxide ions emit strongly in blue. If 3I Atlas has a dense cloud of ionized carbon monoxide surrounding it, that might explain the blue color. But we're back to the same problem. Producing enough ionized gas to create visible blue coloration requires massive outgassing. We've already established that the observed gas production is 20 to 40 times too low to explain the acceleration. Now we need even more gas to explain the color? The temperature argument makes this even stranger. At 203 million kilometers from the Sun, the surface temperature of 3I Atlas should be around 250 to 300 Kelvin. That's cold. Not room temperature cold, but genuinely cold by human standards. Objects at these temperatures emit thermal radiation in the infrared spectrum, not visible light. They certainly don't glow blue. Cold surfaces appear reddish in reflected light. Hot surfaces can appear bluish. 3I Atlas isn't hot enough to glow blue, yet blue it appears. Perhaps the surface composition is unlike anything in our solar system. Perhaps interstellar processing created materials that preferentially reflect blue wavelengths. Perhaps cosmic ray bombardment over billions of years altered the surface chemistry in ways we've never encountered. These explanations are possible but unfalsifiable. They assume unknown materials with unknown properties to explain unknown phenomena. At some point, stacking unknowns doesn't constitute explanation. It constitutes admitting ignorance while pretending otherwise. Let's add one more layer. The trajectory itself has interesting properties. 3I Atlas entered our solar system from a direction astronomers call the local standard of rest. This sounds technical, but the concept is straightforward. Stars in our galactic neighborhood are all moving through space. They have different velocities relative to each other. But if you average all those motions together, you get a kind of cosmic reference frame, the average velocity of nearby stars. Objects arriving from this direction enter our solar system with minimal relative velocity. They're not fighting against our sun's motion through the galaxy. Why does this matter? An object arriving from the local standard of rest spends more time in our solar system than one arriving from a random direction at high relative speed. It enters more gently, curves around the sun more slowly, and exits more gradually. This provides a longer observation window. We have more time to study it. Now, I want to be extremely careful here. Coincidences happen constantly. The universe is under no obligation to make sense to us, and random chance produces patterns that seem meaningful but aren't. The trajectory is what it is for mathematical reasons involving gravitational dynamics and initial conditions we can't know. I am not suggesting the path was designed or intentional, but the observation is worth noting. 3I Atlas follows a trajectory that maximizes our ability to study it. After perihelion, it's heading toward Jupiter, arriving around March 2026. This means approximately 5 more months of observation opportunity. For comparison, Oumuamua was only observable for a few weeks, before it became too faint to track. We're getting much more time with 3I Atlas. Coincidence? Almost certainly. But an interesting one. The Jupiter encounter itself adds another dimension. At closest approach, 3I Atlas will pass roughly 400 million kilometers from Jupiter. That's close enough for measurable gravitational interaction. Jupiter's immense gravity will alter the object's trajectory, changing its exit vector from our solar system. Scientists can use this gravitational influence to learn more about the object's mass and internal structure. More data, more constraints, more opportunity to solve the mystery. Let's step back and consider what we're actually dealing with here. Each anomaly individually might be explained away with enough creativity. Acceleration without proportional outgassing. Maybe some invisible gas we haven't detected yet. Brightness increasing at unprecedented rates. Maybe unusual surface composition. Blue color. Maybe ionized gas emissions. Convenient trajectory. Maybe pure chance. But science doesn't work by explaining each inconvenient fact separately with separate special pleading. Good scientific explanations are unified. They explain multiple observations with single mechanisms. General relativity explains Mercury's orbit, gravitational lensing, and GPS satellite timing with one set of equations. Evolution explains biodiversity, fossil sequences, and antibiotic resistance with one mechanism. Good theories are elegant and comprehensive. What single natural mechanism explains all of 3I Atlas's anomalies simultaneously? What one process produces acceleration without visible outgassing, extreme brightness increase, blue coloration, and happens to affect 2 out of 3 interstellar objects we've detected? No one has proposed such a mechanism. Every explanation addresses one anomaly while ignoring or worsening others. This is where intellectual honesty becomes uncomfortable. When data repeatedly defies your models, you have options. You can dismiss the data, but multiple independent observations confirm these measurements. You can claim measurement error, But different instruments using different techniques yield consistent results. You can keep proposing increasingly exotic natural explanations, but at some point that becomes indistinguishable from making things up. Or you can acknowledge that maybe, just maybe, your models are incomplete. Maybe the assumptions underlying your interpretations need revision. Maybe nature is trying to tell you something you don't want to hear. Avi Loeb articulated this position elegantly at a Harvard lunch discussion about the Hubble tension, an unrelated cosmological puzzle where different measurements of the universe's expansion rate yield conflicting results. Some scientists argued the data must be wrong because theory couldn't accommodate it. Loeb's response was blunt. That's terrible science. You don't get to reject data because your theory doesn't fit. You revise the theory. The same principle applies here. 3I Atlas presents data that doesn't fit our theories. The scientifically rigorous response isn't to dismiss the data or invoke increasingly implausible natural explanations. It's to seriously consider that our theoretical framework might need expansion. What forces could accelerate objects in space besides outgassing? What processes might we have overlooked? What assumptions have we made that might be wrong? These are uncomfortable questions, because they open doors to possibilities that sound fantastical. But science has always progressed by confronting uncomfortable observations. The ultraviolet catastrophe led to quantum mechanics. The constant speed of light led to relativity. Anomalous Mercury orbit led to revised gravitational theory. Every major advancement in physics started with data that didn't fit, and scientists brave enough to take that misfit seriously. 3I Atlas might be remembered as a curious footnote in astronomical history, a weird object that we eventually explained with some clever natural mechanism no one has thought of yet. That's entirely possible, maybe even probable, but it might also be remembered as the moment we first glimpsed something genuinely outside our experience. Not better or worse, just different. And that possibility, however small, deserves serious scientific attention, not reflexive dismissal. The stakes are simply too high for comfortable answers that don't actually fit the evidence. We stand at a pivotal moment in this unfolding mystery. The data has been collected, the anomalies have been cataloged, the calculations have been performed, the pattern has emerged. But the story isn't over. In fact, the most important chapter is about to be written. Over the next several weeks and months, humanity will point its most sophisticated instruments at 3I Atlas and demand answers. What those instruments reveal will determine whether this becomes a resolved puzzle or an enduring enigma that reshapes our understanding of the cosmos. December 19th, 2025. Mark that date. On that day, 3I Atlas makes its closest approach to Earth, passing at a distance of roughly 167 million miles. Still enormously far by terrestrial standards, but close enough for our best telescopes to achieve their sharpest, most detailed observations. This is our window. Our opportunity. Our chance to either solve this mystery or deepen it irreversibly. The James Webb Space Telescope will be watching. This marvel of engineering, orbiting the sun at a point a million miles from Earth, represents the pinnacle of astronomical capability. Its 6.5-meter gold-plated mirror collects infrared light with unprecedented sensitivity. While Hubble sees primarily visible light, Webb sees the heat signatures of cold objects. It can detect the faint glow of gas molecules invisible to optical telescopes. It can identify chemical compositions through spectral analysis more precise than anything we've had before. If 3I Atlas is naturally outgassing, Webb will see it. Sublimating ice produces specific infrared signatures. Water molecules vibrate at characteristic frequencies, emitting and absorbing light at predictable wavelengths. Carbon dioxide does the same at different frequencies. Carbon monoxide, ammonia, methane all leave distinctive fingerprints in infrared spectra. Webb can read these fingerprints with extraordinary precision. The telescope has scheduled multiple observation sessions throughout December and January. Different filters will capture different wavelength ranges. Repeated observations will track any changes over time. The data collection will be comprehensive, methodical, and impossible to dismiss as incomplete. Whatever Webb sees or doesn't see will become part of the permanent scientific record. Hubble Space Telescope joins the campaign. After more than 3 decades in orbit, Hubble remains unmatched for optical resolution. Floating above Earth's atmosphere, it sees with clarity that ground-based telescopes struggle to match. Its cameras can resolve the coma structure around 3I Atlas with precision, measuring size, brightness distribution, and any asymmetries that might hint at the outgassing direction. If a massive gas cloud surrounds the nucleus, Hubble will photograph it. If the cloud is smaller than expected, Hubble will measure exactly how much smaller. The telescope becomes our ruler, our yardstick for assessing whether the observed coma matches the theoretical requirements. Its archives will preserve these images for future scientists to study, analyze, and debate. Ground-based observatories contribute their unique capabilities. The Very Large Telescope in Chile's Atacama Desert combines 4 8.2-meter mirrors with adaptive optics that correct for atmospheric turbulence in real time. Its spectroscopic instruments can identify molecular species in the coma by their characteristic light emissions. The Keck Observatory in Hawaii adds more spectroscopic data from a different vantage point. The Gemini Observatory provides multi-wavelength coverage. Dozens of smaller telescopes worldwide contribute supporting observations. This represents a coordinated global effort. Scientists across continents sharing data, comparing results, checking each other's conclusions. No single telescope's results will stand alone. The convergence or divergence of multiple independent observations will tell the story. What exactly are they looking for? The predictions have been published explicitly. If 3I Atlas is a natural comet experiencing standard outgassing, the observation should reveal specific features. The coma should measure at least 50,000 kilometers in diameter, possibly much larger. Gas production rates should fall between 500,000 and 2,000 kilograms per second during closest approach. Spectroscopic signatures should show water vapor, carbon dioxide, carbon monoxide, and potentially other familiar cometary molecules in abundances matching the mass loss rates. Infrared emissions should indicate surface temperatures consistent with ice sublimation. Dust particles should be visible trailing behind, swept back by solar radiation pressure into a characteristic tail. These are testable predictions, falsifiable hypotheses, real science. If observations match these predictions, the mystery dissolves. 3I Atlas becomes an unusual but natural comet, perhaps composed of exotic, interstellar materials but behaving according to known physics. Headlines will announce that scientists solved the puzzle. Papers will be published explaining the unique composition. Textbooks will add a footnote about the third interstellar visitor. Case closed. But what if the observations don't match? What if Webb sees insufficient infrared emission for the required gas production? What if Hubble photographs a coma far smaller than predicted? What if spectroscopy detects only trace amounts of the necessary molecules? What if every measurement confirms what earlier observations suggested, that the outgassing is grossly insufficient to explain the acceleration? This scenario forces a reckoning. The natural explanation fails not because we didn't look hard enough, but because we looked with the best instruments humanity has ever built and found insufficient evidence. You can't dismiss that by claiming we need better telescopes. These are the best telescopes. You can't argue we looked in the wrong wavelengths. We covered the entire electromagnetic spectrum. You can't suggest measurement error. Independent instruments using different techniques reach the same conclusions. The scientific community will then face a choice. Accept that current models are incomplete and explore alternative mechanisms for non-gravitational acceleration. This might lead to new physics, new understanding of how matter behaves under certain conditions. Perhaps some exotic process we haven't imagined produces thrust without detectable outgassing. Discovery of such a process would revolutionize propulsion technology, or consider more exotic possibilities that the mainstream has been reluctant to entertain. Perhaps some objects in space are not natural formations at all? Neither path is comfortable. The first requires admitting our physics models have gaps. The second requires entertaining hypotheses that sound like science fiction. But science doesn't promise comfort. It promises truth. And truth often arrives wrapped in discomfort. I want to present both possible futures fairly because honest analysis requires acknowledging uncertainty. The story isn't written yet. I genuinely don't know which future will unfold. Anyone claiming certainty at this point is either lying or foolish. But exploring both scenarios helps us understand what's at stake. In the first future, the mystery is solved elegantly. Webb's infrared detectors reveal massive water ice sublimation occurring in deep layers below the surface, hidden from optical view but visible to infrared. The gas production rates match calculations perfectly. Hubble photographs a diffuse but substantial coma that earlier observations missed due to its low surface brightness spread over enormous volume. Spectroscopy confirms familiar cometary molecules in expected abundances. The acceleration correlates precisely with mass loss. 3I Atlas enters history as a fascinating interstellar comet with unusual surface properties, but fundamentally natural behavior. Scientists publish triumphant papers. The anomaly becomes a solved case study in exotic cometary composition. In this future, what do we learn? Interstellar objects can have surface properties dramatically different from solar system comets. Billion-year exposure to cosmic rays and interstellar radiation modifies surfaces in ways we hadn't fully anticipated, but the underlying physics remains unchanged. Newton's laws hold. Momentum conservation remains absolute. Our models need refinement, not revolution. Comfortable resolution. In the second future, the mystery deepens irrevocably. Webb's observations show thermal emissions consistent with only 50,000 to 100,000 kilograms per second of gas production, exactly what earlier observations suggested. Hubble confirms a coma 1/10 the size required by calculations. Spectroscopy finds trace gases but nothing approaching necessary abundances. Every measurement reinforces earlier findings. The acceleration exists. The outgassing doesn't, at least not in sufficient quantity. Headlines read differently in this future. Interstellar object defies explanation. Scientists baffled by anomalous acceleration. Physics models fail to explain visiting object. The scientific community divides into camps. Conservative astronomers argue we must be missing something, that the natural explanation will eventually emerge with better data or cleverer analysis. Progressive researchers argue the data is clear and we should take it at face value, exploring what it implies even if implications are uncomfortable. Papers are published proposing alternative mechanisms, perhaps quantum effects at macroscopic scales, perhaps exotic matter interactions, perhaps propulsion technology not of our making. Each proposal draws criticism. Skeptics demand extraordinary evidence. Proponents argue the extraordinary evidence already exists in the trajectory data. Debates grow heated. Careers are risked. Scientific method itself gets tested. What do we learn in this future? Potentially, we learn that we are not alone in the universe, that other intelligences exist and have technology capable of interstellar travel. This would be, without exaggeration, the most significant discovery in human history. Not because it changes physics, but because it changes context. Everything humanity has accomplished, every question we've asked about our place in the cosmos, every assumption about our uniqueness, all of it reconfigures in light of confirmed extraterrestrial technology. Or perhaps we learn something equally profound but different. New physics, new forces, new understanding of how matter and energy interact under specific conditions. Revolutions in science often begin with anomalous observations that don't fit existing frameworks. The ultraviolet catastrophe led to quantum mechanics, because classical physics couldn't explain blackbody radiation. The Michelson-Morley experiment led to special relativity, because Newtonian physics couldn't accommodate constant light speed. 3I Atlas might lead to something equally transformative. The honest position acknowledges both possibilities without claiming to know which will emerge. The intellectually responsible stance is uncertainty combined with intense curiosity. We don't know yet, but we're about to find out. And regardless of outcome, we're going to learn something important. Let me step back and address the deeper philosophical issue at play here. Throughout this investigation, one voice has consistently advocated for intellectual courage in the face of anomalous data. Avi Loeb's position isn't about believing in aliens. It's about believing in the scientific method itself. When data doesn't fit theory, you don't dismiss the data. You take it seriously. You explore all possibilities. You follow evidence wherever it leads, even into uncomfortable territory. History validates this approach repeatedly. Galileo observed moons orbiting Jupiter in 1610. This contradicted the geocentric model that placed Earth at the universe's center with all celestial bodies revolving around it. The establishment resisted. Careers and reputations and religious doctrines were at stake. But the data was clear. Moons orbited Jupiter. Eventually, the evidence forced a paradigm shift. Heliocentrism replaced geocentrism. Our understanding of the cosmos expanded dramatically. Alfred Wegener proposed continental drift in 1912. He noticed that continents fit together like puzzle pieces. He found matching fossils on opposite shores of the Atlantic. He proposed that continents move over geological time. Geologists mocked him. They couldn't imagine a mechanism. How could solid continents plow through ocean floors? Wegener died in 1930 without vindication. Decades later, plate tectonics emerged as the mechanism. Continental drift became accepted science. Wegener was right. The establishment was wrong. The data was correct all along. Ignaz Semmelweis discovered in the 1840s that hand-washing dramatically reduced maternal mortality in hospitals. Doctors were carrying something deadly from autopsies to deliveries. He proposed basic hygiene protocols. The medical establishment rejected him. Doctors were gentlemen. Their hands couldn't possibly be dirty. Semmelweis was committed to an asylum and died tragically. Germ theory later vindicated his observations completely. Hand-washing became standard practice. He was right. The evidence was clear. The establishment refused to see it. The pattern repeats throughout scientific history. Data that doesn't fit existing models often signals imminent revolution in understanding. The appropriate response isn't reflexive rejection, but careful investigation. 3I Atlas presents such data. Its acceleration defies explanation. Its properties challenge assumptions. Its existence, combined with Oumuamua's similar anomalies, demands serious attention. This doesn't mean accepting sensational. Conclusions prematurely. Extraordinary claims require extraordinary evidence. We don't have conclusive evidence that 3I Atlas is artificial technology. We have anomalous data that natural explanations haven't successfully addressed. That's different. That's the beginning of investigation, not its conclusion. What we're witnessing is science in action. Real science. Messy science. Science that involves uncertainty, debate, and courage to confront uncomfortable possibilities. The coming observations will provide more data. That data will constrain the possibilities. Either natural explanations will be vindicated or they'll fail more spectacularly than before. Either way, we'll know more than we do now. So where does this leave us? Let me summarize clearly. 3I Atlas is accelerating through our solar system in ways that gravity alone cannot explain. The required outgassing to create this acceleration should produce a massive, brilliant gas cloud easily visible to our telescopes. We're not seeing anywhere near that amount of gas. This is the second interstellar object displaying this exact pattern of behavior. Additional anomalies, including unprecedented brightness, increase in inexplicable blue coloration, compound the mystery. We don't know if future observations will find the missing gas. We don't know if some exotic natural explanation exists. We don't know if this indicates unknown physics or unknown technology. We don't know what Oumuamua was. These uncertainties aren't failures of science. They're the current state of an active investigation. What we do know is that this object has given us our clearest opportunity yet to study interstellar material up close. We have months of observation time ahead. We have the most advanced instruments ever built trained on target. We have a scientific community actively engaged with the puzzle. Whatever answers emerge will emerge from careful observation and rigorous analysis. I've presented the data as clearly as I can. I've shown you the calculations. I've explained the anomalies. I've laid out the possibilities. Now you're equipped to follow this story as it unfolds. You can evaluate future observations with informed perspective. You can judge whether natural explanations succeed or fail based on actual evidence rather than blind faith or unfounded speculation. The universe is under no obligation to make sense to us. It is under no obligation to conform to our expectations or fit neatly into our existing frameworks. 3I Atlas might be the cosmos reminding us that mysteries still exist, that wonder still has a place in the age of information, that humility before the unknown remains scientifically appropriate. This might be nothing, a peculiar comet with exotic composition that future analysis will fully explain. Are physics intact? Are assumptions validated? Or this might be something. Evidence that we're not alone. Proof that intelligence exists beyond Earth. Technology traversing the void between stars. The most important discovery in human history. The data will tell us which. Not speculation, not hope, not fear. Data. Evidence. Observation. Analysis. The scientific method applied with courage and honesty. 3I Atlas just accelerated without visible outgassing. Physics says this is impossible. Either physics is incomplete, our observations are insufficient, or something extraordinary is occurring in our solar system. The next few months will determine which explanation holds. Stay curious, stay skeptical, stay open to possibility, stay watching the skies. The universe just sent us a message. We're still learning how to read it.